Okay, so I think everyone's here already, online or in seat. So we'll get started. So first, I would like to take a minute for you guys to help me um, complete or correct the seating charts. Okay, so if you are in Wednesday section, so first bring out the PowerPoint slides of today, and then click on the Wednesday lecture seat chart, and then correct or fill where you are sitting, and then also for the lab section, and then the same for Fridays. Okay, so if you could do that quickly, I'll give you guys like a 1 or 2 minutes to finish that. I think for Fridays, I have everyone put in the seat on the chart, but I'm not sure if I got your seating correctly. But for Wednesday, I have a few of you guys haven't filled the seat. Okay, so if you could do that, that'd be great. And you guys probably know the purpose of this is for contact tracing in case anyone will be positive, test positive, then they will use the charts to trace down who needs to be in quarantine. Okay. And it looks like one of this is loading, or maybe a couple of this is not loading quickly. Yeah, but if you experiencing the same problem I have here, check on again later at some point. Okay, so I think I have 3 of them open up here. Um, just couldn't have this one open. Okay, maybe let me see. Yeah, okay, it goes up now. So all right, okay. Let me see. Oh, Jerry, sitting over here. Changing this over here. Do I get everyone correct here? Okay. All right. So um, today we are going to check chapter 3. And then for the classroom surface disinfecting today's Abigail Lodge and Alyssa Miller. Okay. All right, so in chapter 2, we talk about one-dimensional motion. So then the motion is very simple. You are just, the object is just moving in one direction, okay? But in most cases, say if you want to go from particular point to another one, say if you are in a downtown area in some city, if you want to go from like say like McDonald's to somewhere else. Okay, so most of the time you couldn't get to your destination just in one direction. Okay, so you might have to go in one direction and then in another direction. Okay, so not turning back, but turn slightly, say 90 degree to another direction. Okay, So most of cases, the motion of the object could be in two-dimensional, all right, or maybe in some cases it could be in three-dimensional, all right. So let's the focus of this chapter here, okay. So in that case, then the displacement or the change of position of the object, you can clearly see if you go from this point to that final point, you go on this part of the journey first and then the second part, which is perpendicular to the first part. Okay, if that's the case, then you can use Pythagorean theorem to determine what's the displacement, the length of it, okay, which is the hypotenuse of this right angle triangle, okay. In this case, specifically, if you go 9 blocks east and 5 blocks north, then you can calculate using the Pythagorean theorem, it will give you 10.3 blocks, okay, for the magnitude of your displacement. Okay, so as I said, many times the motion is in two-dimensional. For example, like the helicopter here in this slide. Okay, if you are walking from starting point to final point, you will have to go in this direction first, and then in that direction. Okay, but if you are riding a helicopter, then you can go straightly from here to there. Okay, but in this case, then you can see then the motion of the helicopter, it has two dimensional motions simultaneously. So one is to go along the x-axis or the eastward direction, okay? And then at the same time, it's moving in the northward or the y direction, right? So for the helicopter, if you have a 2D coordinate system like this, or using the northeast and north, south, and west, east coordinates. So then the motion of the helicopter is simultaneously in x direction and also in y direction, right? So if that's the case, then you can actually break the motion of the object into two dimensions, okay? So say one part is going in x direction and then the other, or one component is going in one direction and then the other one is going in the other direction, okay? Just like if you are roller skating, and then at the same time, if you are dribbling a ball, okay? So you can see if you are roller skating, you are going in one direction, okay? Now, for the ball, if you are dribbling the ball, then it kind of actually just going in one direction if you are holding the ball. You can see that you throw it down as you move, and then it will end up in your hand when it bounces back, right? So in that sense, you can see, or you can, when you are standing right here, you can dribble the ball, it will go down and then bounce up into your hand at the same time, okay? So you can see these two motions, they are actually independent of each other, okay? It's not going to be affected. So the y component motion will be independent of the x component motion, okay? So doesn't matter if you're walking and then dribbling, or if you are just standing here and dribbling your ball, okay? It's going to be ending at your hand at the same time, okay? Or on these cases, if you are having a skateboard, all right? And then at a certain point, you jump up, all right? And then you're going to land on the skateboard again later on, right? Because the horizontal motion of the ball, now it's not going to be affected by the fact that you are jumping up, okay? So then your body, at this time, if you jump up, then we'll have motion in two-dimensional, one in the horizontal direction and then the other on the vertical direction, okay? So now you are giving your body a vertical motion, it will not affect the body's horizontal motion because you can see you are landing back on the skateboard. So that means your body's horizontal motion is still going in that direction with the same velocity or speed, okay? Indicated by landing back on the board there, okay? Similarly for other two scenarios, okay? So the same here. All right, so if you have a two-dimensional motion, if you break the motion into two components, the one as horizontal component and one vertical component, so these two have to be perpendicular to each other. So then the two motions are not dependent, okay? So they are not affecting each other, all right? So then knowing that, it makes our understanding of two-dimensional motion a little bit easier because we already learned how to deal with one-dimensional motion, right? So then for two-dimensional motion, you just break the motion into X and Y component, or X dimension and Y dimension, right? So then you just have to repeat the whatever you were doing in chapter 2 like twice, okay? So one in horizontal direction and then the other one in the vertical direction. Let me check if the camera is set up right for the online folks. Okay, it may not be perfect, but all right. Okay, so that's first section of this chapter. So I'm talking about two-dimensional motion, and then we know now you can break the motions into two dimensions. So then it's just doing one-dimensional motion twice. Okay. The second chapter here talks about the vector. Okay. So we talked about vector in the previous chapter. Any quantity that has, if you want to describe it, you need a magnitude and direction. So then it's a vector quantity. So in this case, and then in chapter 2, we talk about just vector in one dimension. So the displacement in one direction, velocity in one direction, and acceleration in direction. In that case, you can use positive and negative to indicate the direction, okay? Now, for two-dimensional vector, it's going to be a little bit more complicated than that, okay? You cannot simply use positive or negative to indicate the direction, okay? Because now in this case, your direction could be in 360 degrees, right? It could be like in one particular direction, it could be having an angle with that direction, say X direction. It could be just in X direction, right? It could be in Y direction, and then the minus X, etc. So if you are referring the direction to the positive axis, which we'll talk about this angle called directional angle, then it could be anything between from 0 to one full circle of 360 degrees, okay? All right, so then we want to be careful about the vectors here. The first thing to notice that you can use, again, the letter to represent it's a vector. So in this case, if it's in typing, then a D with the boldface letter or any letter with boldface that indicate a vector. Or you can do the letter with the arrow on top that also indicate a vector. Okay, so that's pretty much done in writing. So these are the two types of symbols people use to indicate it's a vector quantity, okay? So I think when you are in guys writing, you pretty much put an arrow on top of letter, then that means it's a vector quantity. Now it doesn't matter if it's a capital letter or lowercase letter, okay? So as long as boldface in typing, then it's a vector, or if you are in writing, you put the arrow on top, it's a vector, okay? So for a vector, the magnitude of the vector, so then can be represented by the symbol in italics. Okay, so the letter D, the italic form D, then that means it's the magnitude of it. Okay, and then the direction of it is typically represented by the angle with a certain axis. Okay, referring to a certain direction. For example, the positive X or positive Y, or negative X and negative Y, okay? And then also in some problems, it's also with respect to either the eastward or northward or west or south, okay, word, okay? So in this textbook, or in many textbooks, okay, the preferable angle is called directional angle. That is the angle between the vector and the positive X axis, okay? Unless otherwise specified the reference line is. So then it will be directional angle will be this angle, okay? So you can see directional angle can be from 0 up to 360 degrees. Or sometimes if a vector is below the positive axis, then people sometimes would just say, for example, if you have X vector in this direction, people would just say, okay, the directional angle is negative, say, for example, 30 degrees or 29.1 degrees, okay? So that's fine too, all right? All right. So, so for a vector, if you draw it on graph carefully with proper scale, okay? So then, for example, for the example we look or the figures we checked earlier a couple of times, if you walk from one point to another point, okay, you are actually having two parts of your journey. You go in X direction first, and then you go in Y direction, okay? So if we do the vector in graph, then you'll just put your first displacement vector for the first part of your travel here, all right? And then you are going to just put the second vector in that fashion, all right? Once that is drawn, then you can actually measure the length of resultant vector, and then also use a ruler for the magnitude, and then use a protractor, you can measure the directional angle, okay? So let me see. Yeah, so this is one way of how you want to do two vectors, or if you have a journey that is consists of two paths, then you can do the two displacement add up, okay? I think we will talk about more details later on, okay? But let's look, take a look on several of the characters of the vectors, okay? So for a vector, we say you can describe a vector completely by specifying its magnitude and direction, right? So then only those two quantities matter. So you can move a vector parallelly over any place on this two-dimensional plane, right? You can move this guy parallelly over there. So then you still have its original length and then its original direction, right? In that direction, because direction is specified by the angle between the vector with a reference line. So then the angle will not change if you just move it parallelly over, right? So then you can move it anywhere, okay? So in that case, all these vectors are their identical vectors, okay? So this vector is the same as that one, as this one, as this one, and then whatever, okay? So you can move a vector parallelly to any location, all right? Then you'll have identical vector, as long as you keep the magnitude and direction the same, okay? So that's very important when we are doing vector addition later on, okay? So vector addition, the first way to do is doing it graphically, okay? Meaning you are drawing out the vectors on a piece of paper two-dimensionally with proper scales and their angles represented correctly, okay? So this is called head-to-tail method, okay? So again, use the example of you walk in a city, you have to walk first in the X direction and then secondly in the Y direction to get to your final destination over there. So then this is like adding one displacement to the other displacement, okay? So the first displacement that is 9 units in X direction, the second one is 5 units in Y direction, okay? And then this will be your resultant, okay? So the way to do two vector addition, so this is just one example, but in general, you might have two vectors, say one vector that is pointing in that direction with specified units, okay, and then the other vector going in that direction, right? So you may be doing this vector plus that vector, okay? So graphically way, you can move this vector parallelly over here, okay? And then that will be your resultant, okay? So now for a vector, let's talk about two more terms here. For a vector, the starting point of the vector is called the end of the vector, okay? And then this is called the head of the vector, okay? So the ending point, you'll use an arrow here to indicate that's the ending, okay? So starting from here and then ending over there with an arrow, okay? So when you move the second vector parallelly over, so you place the tail of the first vector of the second vector at the head of the first vector, okay? So the tail of the second vector, then you place it at the head of the first vector. Then your resultant vector is starting from the tail of the first vector pointing towards the end of the second vector or the head of the second vector, okay? So from the tail of the first vector pointing to the head of the second vector. Okay. Now, if you do this with proper scale, then you will figure out, okay, again, you can use a ruler and projector to measure the magnitude of your resultant vector and then its directional angle, okay, made with respect to the positive axis, okay? So this is called the head to tail method, okay? All right. Now, when you have a vector, say vector B, okay, and then if you change the direction of vector B, okay, if you are, so this is the tail of the vector B, this is head of it. Now, if you switch the head and tail, so what happens? Now you have a new vector points from the head of the B vector to the tail of the B vector. So then you will have a negative B vector. Okay, so that means you change the direction. If you change the direction, then it's going to become a negative of itself. Okay, so if the direction is reversed, the magnitude is still the same, then you have a negative B vector. Okay. So a negative sign in front of vector will change the direction of the vector by 180 degrees. Okay. If you multiply a vector by a scalar, okay, say 3 or -3, so if it's a positive number here, then it will not change the direction of the vector, okay? So if this is A, then this will be 3A. So only the magnitude of the vector A will be multiplied by the scalar, okay? So the magnitude becomes 3 times of the original, but direction is the same. Now, if this multiplier is a negative number, then the direction of the vector changes by 180 degrees, and then the magnitude is changed also by this number, okay? So -3 will be multiplied by 3, okay? So pay attention to the multiplier. If it's a negative number, it not only changes the magnitude, also changes the direction. Okay, so knowing that, then we can do vector subtracting. Okay, so if you are doing A minus B, then that is equivalent of doing A plus minus B, right? So for example, if this is A vector, this is a B vector, okay? So then if you are doing A minus B, that means you are doing A plus negative B, okay? So a negative B, then you place the tail of this second vector. If you are doing A plus B, then this is your resultant, okay? So again, this is how you would do graphically. You place the tail of the second vector at the head of the first vector, then resultant is pointing from the tail of the first towards the head of the second, okay? So then you'll get your resultant vector that way, okay? So in that sense, then adding two vectors or subtracting one vector from another, you can do them in a similar fashion, okay? Graphically. All right. So when you are expressing your vector, as I said, you can use a magnitude, you can use a directional angle, okay? So that's why I mentioned earlier, that is one of the ways to do it, okay? So in this case, if you have a R vector, so R with a hat, with the arrow, that means a vector. Now, its magnitude, then it's just italic R, okay? Without an arrow on top, that's the magnitude. Directional angle is 25 degrees with respect to X, okay? So this is one of the ways expressing it. You can also do components, okay? You can specify its components. So then the X component of this R vector, all right? So then it's 0.997 meters. And then the Y direction, Y components of this guy will be 0.465 meters, okay? If the magnitude is 1.110 and then the angle is 25 degrees, you can figure that out, okay, by looking at the geometry here. So it's basically this R magnitude times cosine of the angle will give you X component, and then the magnitude times sine of this angle will give you this Y component, okay? So if a problem doesn't ask you specifically how to express a vector, you can do either way. You can say what's the magnitude and then what's its directional angle, or you can say what's its x component and what's its y component. Okay. All right. So then these are the formulas you can use to um, get the information from one way or the other. Okay. So if you are given the magnitude and directional angle, then you can figure out its x component and y component by using these two. Okay. So basically, a cosine angle, directional angle will give you x component, and a sine of angle will give you y component. Okay. Now, these two expressions only apply to when you have this theta defined as the angle of the vector forms with the positive x direction. Okay. Now, many times in a problem, the angle theta may not be defined in that way. Okay. So for example, in a problem, the angle might be defined as the between the vector and then y-axis. Okay. Then you want to be careful about using this. Okay. And then in that case, you'll do sine for the x and then cosine for the y. Okay. But it's geometry. Okay. From the trigonometry, you can figure that out. Okay. All right. And then if you are given the x and y components, you can figure out the magnitude and then directional angle by doing this. Okay. So in some problem, you'll just you'll know the x and y components, and then you can calculate for the magnitude and directional angle. You can actually figure out x and y component first, okay, and then calculate the magnitude and directional angle. All right. So let's have a practice problem here, saying if you have a vector, you know the two components, then what's the magnitude and the angle of this vector make with the x, positive x. Okay. So now in this case, you are just asking by the directional angle the vector makes with the positive x. So that means the theta. Okay. So you guys can use the formulas in the previous slides to figure this out. Okay. So go ahead and give it a try. We can check on the solution together in a couple of minutes. Okay. So by the way, I have homework 3 problems posted online on Expert TA. You guys can start working on the first 2 or 3 problems after today's lecture. Okay. It's this time is still on Thursday next week. Okay, because we'll probably take 4 lectures to finish this chapter. So then I put the due dates 2 more days for the due date. Okay. All right. So I'll wait another 30 seconds or so before we look at the solution together. Many of you guys have submit your responses. Okay. Okay, so let's take a look. So we know that the x component is given as 22 meters, y component is given as 30 meters. Okay, and then we are looking for the magnitude, which is expressed just in the italic form of the letter, and then the theta angle, directional angle. Okay, so you can figure this out, the magnitude, by just using the x component square plus the y component square. Okay, and then directional angle as tangent inverse of y component over x component. Okay, so I think it's straightforward here. So a should be equal to square root of 22 meters square plus 13 meters square. Okay, so I think it's 25.55 something. Okay, so roughly 25.6 meter, or if you want to keep two sig figures, because the two quantities, known quantities, are in two sig figures, so you can say almost 26. Okay, or either this one or that one. At this point, it's not so critical for expert TA. I think it's more likely going to take this number. Okay, if this is not taken, then you will take that for sure. Okay. So this is A. For directional angle theta, it's going to be tangent inverse of 13 over 22. Okay, so remember, it's the y over x. All right, it's not x over y. So then this will give you 13.6 degrees, or roughly 31 degrees. Okay, I see many of you guys got that one right. All right, now if you don't get this number, if you are given, if you got some number like much smaller, say, I don't know, maybe 3, 4, 5, 6 or whatever, check that your calculator is in degree mode, not in radian mode. Okay, so for the angle, it has degree mode or radian mode. Okay, so I think most of the time we are going to deal with degrees. Okay, but if the problem gives you the angle not in degrees, then you want to put that in radian mode. Okay. Any questions you guys might have? For online folks, you can unmute yourself and speak up. Okay,
I actually have a question.
go ahead.
In this particular problem, how do we determine which one will be X and which one will be Y? Is it just the longer one, or because I'm not seeing? Oh, never mind. I see it. Sorry.
All right, that's fine. Yeah. So the question was, how do we determine which one is X component and Y component? So she didn't realize it's specified there. Okay. So yeah. All right. Okay. So so earlier we talked about you can actually do the vector addition graphically. Okay. So that is to keep a proper scale, and then for the magnitude and also the angle. Okay, so that's how you can do it. But you can also do in vector addition analytically. That means looking at the x and y components and work on the numbers. Okay, so if you have a vector and b vector, if you are looking for a vector plus b vector, then you can simply add the x component up and then y component up to be the x component for a resultant vector and then y component for the resultant vector. Okay, so in this case, okay, so this is a vector, this is b vector. You can figure out its x component and then y component. Okay, and then the b component and the x component for b and y component for b. Okay, so then the resultant will be the c vector pointing from the tail of the first vector to the head of the second vector. Its component, it's going to be simply the x component of resultant is the a component x plus b x component. Okay, and then the y component is the ay plus by in that fashion. All right. Once you have determined the Cx and Cy, you can calculate the magnitude for C just doing the square root of Cx squared plus Cy squared. And then directional angle, you can do the same as tangent inverse of the C component, Cy component over Cx component, okay? So that's how you can do vector addition analytically. All right. So we'll have a look on one example here. So I'm going to yeah, I think I can show you how to do the analytically way quickly, okay? And then you guys can give it a try on the, or I'm going to just do the graphically way quickly, and then you guys can give it a try on the analytical way, okay? So you are given two vectors, all right? A 40 millimeters and then 20 degrees. So let me find a protractor here and then a ruler I can use to do it here. So I'm going to show you how to do this. All right. So first you want to set up your XY coordinate. Okay. So you do X. Okay. This is your X component, and then your Y component. Now we can do a 90-degree to it. Okay. To be the Y component. Or X and Y coordinate system. Okay. So this is your Y. You have a vector which is 40 meters and then 20 degree below. Okay. So then first you want to find 20 degree below this guy. So put your protractor over here and then do a 20 degree. So it's going to be in that direction starting from the origin. Okay. All right, and then this is 40. So let me use 4 centimeter for 40 in that case. So I'm going to just draw it up to here. Okay, so that's indicating this is 40 meters. And then this is 20 degree below, okay? So you can say 20 degree. But you should keep in mind, then this is a vector, okay? So the magnitude of a is 40 meters, okay? So then directional angle for a, theta sub a, this should be negative 20 degree or 340 degree, okay? Either way, they will give you the same result for the components, okay? X and Y components. Better than that way. All right. Now the B vector, which is 75 degrees by 50 or 75 meters by 50 degrees above the X. Okay. So first you want to find its direction. Okay. So let's find the 50 degree. So 50 degrees somewhere in that direction. Okay. Maybe make a start there. And then I'm going to do 75 centimeters or 7.5 centimeter as the 75 meters. Okay. So I can do it that way. So in one of the labs, you are going to do the vector addition graphically and then also analytical way. So this is how you want to do it as well. Okay, so you want to be very careful about the angles and then the directional angles. Okay, so this is B vector, and then magnitude of B is 75 meters. Theta of B, then this is positive 50 degrees because it's above the x axis. Okay, all right. So if you are above, you are positive. If you are below, you are negative. Okay. Or you can say if this angle is measured from the x angle counterclockwise, then that's to be positive, and then clockwise you can take negative. Okay, so you can do it also that way. All right, now we are looking for vector, I think a plus b. Yes, the new resultant vector a plus b. Okay, and then to do this analytically or graphically. So what we need to do is, so a plus b, then you move the second vector parallelly over, so its tail is at the head of the first vector. Okay, so you're going to move this guy parallelly over. You can use the ruler and then just move it parallelly over. Okay, somewhere here. So when you are doing this, sometimes you will get the angle off. Okay, but do as much as you can, so then you can do it this way. Again, 75, 7.5. Okay, so let me see. Yeah, up to 7.5, because I'm going to put an arrow on top of it. Okay. So then this is my B vector. All right. So I move the B vector parallel over with the same length and then same direction. So you can double check with this angle. This should be again about 50 degrees. Okay, so 50 degrees there on your protractor. Okay, then your resultant vector should be from here to there. Okay, resultant will be the tail of the first vector pointing to the head of the second vector. Okay, so this will be your resultant C vector. Okay, now if I have done this correctly, I can measure roughly what will be this C vector, the magnitude of it. Okay, so it shows me like about, if you can read clearly, so this is 9.5 and then almost 9.6 something. Okay, so I can do estimation. I can, from graphically where I can tell it's like 96.3 maybe or 0.2 meters. That's how I read from my scale, because my each 1 centimeter is 10 meters, right? Now I can use my protractor to read the angle of this resultant vector. Okay, so you can do, so this is roughly 26 degrees. Okay, it says about 26. You are reading from the inner here. I think it's not so clear, but this is 20, 21, 22, 23, 24, 25, 26. Roughly 26. On the C, this is C vector, resultant C vector. Angle of the C is roughly 26 degrees. Okay. All right. Now, Papi says you can do this with component method. That means you are doing X and Y component, you're adding them up. Okay. So let me see. It looks like, all right, I'll give you guys a couple minutes to maybe get started, okay? And then I will show you the solution in a couple minutes, okay? So you don't have to submit your answers or whatever. I don't think you have enough time to finish them, okay? So just use a couple minutes to understand the problem and then figure out how you want to get started, okay? Or have a plan how you want to solve for this one, and then we can look at the solution together, because we are, looks like we are running close towards the end of the class. I'm showing on my end the PowerPoint of the previous slide before the problem. Okay, so online folks, you can check on the PowerPoint slide one page before on the using components to do adding vectors using components. Okay, so this is basically how you guys want to do it. Okay, you have the x, y, you have the a vector and b vector, you know their magnitude and direction. So first thing you want to figure out is their components, the x component, y component of the two vectors, okay? And then for your resultant vector, you are going to do the two components, x component add up to be the x component of resultant, and then the y component of the original two vectors add up to be the resultant y component, okay? Once you have the y component for the resultant, you can calculate its magnitude and directional angle. Okay, so we will take a look here together on the solution here. Okay, so first thing I want to do is I want to calculate my x component for A. All right, and then my y component for A, and then my B component or x component for B, my y component for B. So these are the four we want to calculate first. Okay. All right. So then AX will be A times cosine of the angle of A, okay? So you'll do 40 meters times cosine of negative 20 degrees. That will give you 37.58 meters, okay? For the Y component, you are doing A sine of theta A, which is 40 meters sine of negative 20 degrees. That will give you minus 13.68 meters, okay? And then B component will be B cosine theta B, 75 cosine of 50 degrees, okay? That will give you 48.21 meters. BY will be B sine of theta B, that will be 75 meters, sine of 50 degrees, okay? So that's 57.45, okay? So then you have the components, x and y components for A and x, y component for B, all right? Now, for the components for the resultant, x, cx, then will be simply ax plus bx, okay? So I think it's straightforward, just a little bit tedious. You will have to do multiple steps here. 37.58 meters plus 48.21 meters, okay? Which gives me 85.79 meters. And then the y component for a resultant is going to be ay plus by, okay? So ay is negative 13.68 plus by is 57.45 meters. That would be 43.77 meters, okay? Now you have the xy component. You can figure out its magnitude by doing simply square root of the x component square plus y component square. So 85.79 meters square plus 43.77 meters square, okay? And then take a square root of it. Now, the resultant is 96.31 meters, okay? If you are careful about the sig figures, so all the quantities were given in 3 sig figs, so then you keep 3 sig figs for your answer, okay? Now you can see when we did this graphically way, we just took a measurement of the length, right? So this one is the same as this one, okay? So that means we did it very good, okay? But it's okay, sometimes it's off by slightly, say 96.1, maybe you measured, when you measure it says 93.1, okay? So that's fine, it's close enough, okay? All right. Now on a directional angle, you will do tangent inverse of cy over cx. Okay, so then tangent inverse of 43.77 over 85.79. Okay, that gives you roughly. Okay, so then in this case, it looks like I'm off when I'm doing it graphical way. I probably didn't do it perfectly parallel over, maybe off by 1 degree or so. So I got 27 degrees. Okay, then when we measure it, it shows like 26 degrees, but it's close. Okay. All right. So this is how you wanted to do this analytically way. Okay. Um, yeah, just tedious. But one thing to remember is if you are using these equations, the a sine, a cosine for the x component, and a sine for the y component, then you are referring to the angle the vector makes with the positive x. Okay. And then for the angle, if you are measuring counterclockwise, that means positive. If you are going clockwise, then that means negative. Okay, so this way is positive, this way is negative. Okay, you are below, you are negative, you are above, you are positive. Okay, so this is one thing to note. A lot of times, many times, when the angle is not given with respect to x, positive x, okay, then you can convert the angle into this. Okay, so for example, let me just throw out the example somehow. Say if you are given a b vector, it says b vector makes an angle with y of 40 degrees. Okay, so then you need to figure that its directional angle then would be the 90 minus 40, which is 50. Okay, in that case, if you are given like this as the angle. All right, or sometimes it's given as like this is the angle, say 40 degrees. So then you want to measure from the positive x over here to add 90 degree to it to be 130. Okay, so pay attention to how the angle is given to you. Okay, when you are utilizing these expressions. Okay, all right. Now I think we have a couple slides just remaining. All right, one thing I would like to point out when you are using your calculator to figure out the directional angle. Okay, so for example, if you if at end of your calculation you were able to figure out the x and y component, okay, so just like what we did earlier, then now in the example we had both x and y as positive numbers, the components as positive numbers, right? So when the scenario, when you have one component is negative here, okay, so when you say tangent inverse in your calculator, it's going to calculate this over this first, okay, so that becomes -2. Now tangent inverse of -2, it doesn't have information of either this is negative or that is negative. Okay, it could be the same, like -1 divided by 0.5, right? Also gives you that. So by default, the calculator will not distinguish that. Okay, so then it might give you a false number, -63 here, because if you look at this, if x is negative, y is positive, then your vector is in the second quadrant, right? But it will give you a negative number. So that means it's giving you the direction in this way, which is below x, okay? So it tells you it's -63, so it's not correct, all right? So in that scenario, you want to check, always just check one component, the x component, okay? If you have x component be negative, then the result you get from your calculator, you want to add 180 to it, okay? So pay attention to that. Once your x component is negative, then your directional angle, when you calculate tangent inverse from your calculator, you need to add 180 to it. Okay, so this is the sum of rule here. Okay. All right. And then you can also cross-check the components you have, and then briefly put them in the XY coordinate system to see which quadrant the vector falls at, okay, to double check your answer, okay? All right, I think we'll stop here for today unless you guys have questions. Any questions you guys might have, you can ask me now. All right, otherwise, see some of you guys for the lab in this afternoon, and then the rest of you guys on Friday.
I have a question about lab on Friday.
Yes.
So I know you mentioned that if one of us were quarantined, that one would be in class and one would be online taking the measurements. However, both of us are actually in quarantine. So how would
Right.
you like us to go about lab?
So for right now, only a couple of you guys are in quarantine. I will not worry about right now. So the thing I proposed was when we have many of you guys are in quarantine, because we do have 2 weeks makeup lab later on in the semester. So if you just miss 1 or 2 labs, then we don't worry about that, okay? So if you are in quarantine and will miss more than 2 labs, then we'll think about the alternative of that, okay?
Okay.
All right.